Welcome to this edition of Lakeside Physics. This video will give an introduction to the basics of gravity. Now, gravity is something that you have long known about. Here are my boys talking about it.
Hey, I have a question for you boys.
What?
Why did that ball fall?
Because I let go.
Yeah, but why does it go down towards the earth?
Because of gravity.
Because of gravity?
Yeah.
Wait, hold on. What do you know about gravity, Evan?
The more gravity, the harder it pulls down. The less gravity, the less it pulls down.
Let's work to develop a deeper understanding of gravity. So Newton's law of universal gravitation describes the force between any two given masses. So let's consider for a moment what this force might depend on. Take a moment, pause the video, and think about what it might depend on. Well, it makes sense that it depends on the two masses. Bigger the mass, bigger the force. You might also reason that it depends on the distance the two objects are from each other. The further the two objects are away from each other, the smaller that force should be. And we do indeed find that the force of gravity is directly proportional to the mass of each object, m1 and m2, and inversely proportional to the distance between the centers of the masses of the two objects, squared. Now, we say it's proportional to, we now can consider that it's actually equal to some constant times m1, m2 over r squared. This constant g is equal to 6.67 times 10 to the minus 11th. The units are newtons, meters squared over kilograms squared, and it's an experimentally determined constant. One of the most precise measurements of G actually occurred here in Seattle at the University of Washington. Ask Dr. Butler about it. His advisor was the principal researcher on the experiment. Some things to consider. First, mass creates gravity. All masses are attracted to all other masses. That even means that you are attracted to your table mate. The force of gravity is a fairly weak force. The law of universal gravitation only applies to spherically symmetric objects and objects where the distance between them is much greater than the size of the objects themselves. Now note, while this is true, and we use gravity all the time on objects like people on the earth, we will often be able to approximate objects to be symmetric and approximate distances to be large. So let's do an example problem. The little prince, who has a mass of 5.0 times 10 to the first kilograms, or 50 kilograms, is standing on planet X. Planet X has a mass of 5.98 times 10 to the 24th kilograms and a radius of 6.38 times 10 to the 6th meters. What is the force of gravity acting on the little prince by planet X? Pause the video and go ahead and try to solve for it. Alright, so you should have used our universal law of gravity, big G times m1, m2 over r squared. And if you plug this in, you should have gotten 490 newtons, and that would be 490 newtons down towards the planet X acting on the little prince. Note that we just plugged in the radius of planet X as our distance from the center of the little prince and planet X. Why didn't we have to worry about the height of the little prince or try to make it to the center of his mass? Well, if you think about it, the size of the planet is very large, so the small addition of his height, or the distance to his center of mass, would be very small compared to that total distance. So, I want you to stop for a moment, and if you had difficulty with this, there are a couple things to consider. First, did you square the distance? Second, did you enter exponent notation correctly? And third, one thing to think about doing is to ignore the units when you're trying to solve. They just kind of make things messy. So right now, I'm going to go ahead and solve it for you using a virtual calculator and give you a couple of hints about techniques for solving when you have big numbers and really small numbers. Alright, so let's go ahead and plug this into our calculators. The first is that you'll want to learn how to use the EE button. So as I go to write 6.67 6.67, I'm going to use, instead of going times 10 hat negative 11, I'm just going to use exponential, scientific notation and go second double E. It's going to stick this little E on there, and then I just write whatever my exponent is going to be. So 6.67 e to the minus 11th times 50 times 5.98, again second E to the 24, divided by 6.38 e to the 6th, and then I will just square that radius, that distance between the two centers. Notice that this makes it really simple because I don't have to worry about any sort of parentheses. When I use this scientific notation format, it considers this entire number to be one thing. So when I go to square it, it's going to square that entire number. So I hit enter, and I do indeed get 400, rounded to 490 newtons. All right, so let's continue our problem. What is the force of gravity acting on planet X by the little prince? Well, according to Newton's third law, the force should have the same magnitude but in the opposite direction. So we should have 490 newtons upwards acting on planet X. Now let's take little prince and take him and stick him on the planet Earth. What should his weight be? Well, we know that the force of weight is equal to m times little g, so 50 kilograms times 9.8 meters per second squared gives us 490 newtons. 490 newtons downward? That sounds a little familiar. Well, we must have done something similar to what's on Earth. And in fact, surprisingly so, planet X has the same mass and radius of our own planet Earth. So we've been using the force of weight and force of gravity interchangeably. They are equivalent. Imagine placing a box of mass m on a planet of mass m2 and a radius r. Well, the force of weight should be equal to the force of gravity. The force of weight is going to be the mass of the box times little g, and the force of gravity is the big G, mass 1, mass 2 over r squared. So we see that the masses cancel out, and little g is actually just equal to our big G, or the constant, times the mass of our planet divided by the radius of the planet squared. Notice that this provides a method that could be used for finding the mass of the Earth. Let's do one more example problem. A box weighs 24 newtons on planet A. I take it to planet B, which has twice the mass of planet A and twice the radius of planet A. How much does the box weigh on planet B? Pause the video now and try to solve this. Well, the force of gravity on B is going to be equal to big G times the mass of the box times the mass of planet B over the radius of planet B squared. We can replace the mass of B with 2 times the mass of A and replace the radius of B with 2 times the radius of A. Now, if I pull out these factors, I end up getting 2 divided by 2 squared times what is the force of gravity on A. So I end up getting 1/2 what the weight of this box was on planet A, or 1/2 of 24, which gives me 12 newtons. Note that we can think about this in terms of proportionality. So as I double the mass, I double the force. If I double the radius, I make the force 1/4 the size. The combination of the two results in the force being half of its original. That concludes our discussion on gravity. If you have any questions, please let us know. Thanks. So now let's consider circular orbits caused by gravity. So when we talk about circular orbits, we're talking about, for example, the moon orbiting around the Earth, or the Earth orbiting around the Sun. It is the force of gravity that acts in this case as the centripetal force for the orbiting objects. Now, you might ask yourself, why is it that the moon doesn't go crashing into the Earth if there's this force of gravity pulling the moon towards the Earth? Well, it's the same idea as when we think about a ball being swung in a circle and that there's tension inward. Why doesn't the ball end up flying towards the center of the circle? It's because the object is in motion initially, and so that force is causing it to change directions off of its original path. So if the moon wasn't moving, it would go crashing into the Earth. For circular orbits, the orbiting object must have a constant speed. This requires two things. One, that the velocity vector is perpendicular to the acceleration vector, and two, that there are no other forces present. For real orbits, these two assumptions are generally not true. The reasons are, most objects have elliptical orbits where velocity is not perpendicular to acceleration, and other forces are generally present. Other forces due to planets, dust, atmospheres, etc., causing the orbits to decay. We will only be considering circular orbits. So let's do an example. Here's a simple orbit. Imagine that the space shuttle Atlantis is in a circular orbit at 150 kilometers above the surface of the Earth. The mass of the Earth is given and the radius is given. Pause this video and try to see if you can figure out what speed Atlantis must be traveling at to be in this orbit. All right, so here's the solution. First, we need to think about the free body diagram. Of course, it's just the force of gravity in this case. And so if we think about writing a net force equation, our net force is equal to Fg, and this is equal to mv squared over r. But we also have a new equation for Fg, big G m1 m2 over r squared. Now notice that the mass of the orbiting object cancels. So because of this is the mass of the rocket is what is in mv squared over r, it is the one that cancels, and we're left with v squared over r equals big G times the mass of the Earth divided by the radius of the circular orbit. Notice that this radius of the circular orbit is also the same thing as the distance between the centers of our two objects. We can simplify this and then plug in our values, and we end up getting that the speed is 7,800 meters per second. Let's consider another question. Now let's imagine that the satellite orbits the Earth at twice the distance of Atlantis. Would the satellite's speed be more, less, or the same as the shuttle? Consider the equation we generated for part B. V squared equals G times mass of the Earth divided by r, so as r increases, the speed will decrease. Notice again that this is completely independent of the size of our object, the mass of the orbiting object. All right, now let's imagine that there is an astronaut in Atlantis. What is the force of gravity acting on the astronaut? We have Fg equals big G m1 m2 over r squared, and we can plug in our values for when it is 150 kilometers above the surface of the Earth, and we'll get 610 newtons. For reference, on Earth, this astronaut would have have a weight of 640 newtons. That's not really all that much different from if it was at the surface of the Earth. Again, that's because 150 kilometers is a small fraction of that total distance to the center of the Earth. All right, so now what would happen if an astronaut were to stand on a spring scale in the Atlantis as the shuttle orbits the Earth? What would the scale read? Well, if you recall, a spring scale measures normal force. According to our free body diagram, there is no normal force. So the scale must read 0 Newton. So we have come to an end on this video of circular orbits and gravity. Please let me know if you have any questions. Thanks.